All right, so we just worked through this example and we rejected the null hypothesis and said at least one pair of um, means were different from one another. And so let's say we hadn't rejected the null. So if we fail to reject the null hypothesis, well, then there's nothing else to do. We would just stop because there's no evidence that the means differ, and that's that. So we would just say the means are not different from one another. Let's say we do reject the null like we did in our example, and we accept the alternative hypothesis. Well, then what do we do? So what we said is that we concluded that at least one pair of means differ from one another. But the question now becomes, which pairs are different from one another? Because in our example, we've got four groups, but we have no idea which groups are actually different from one another. So that's where we're going next. So one idea we might think is to perform a bunch of pairwise t-tests like we did in chapter 10. So the question is, why don't we just do a bunch of t-tests? And the answer to that is that we have a problem. And our problem is that we are doing multiple comparisons. So recall that the probability of a type 1 error for a single test is alpha. But when we perform multiple tests, well, then we're going to see our type 1 error rate is actually equal to this, 1 minus alpha to the k for k comparisons. So let's illustrate this. So let's just use alpha is equal to 0.05. So k equal 1, so this would be chapter 10, so just one comparison. We would have 1 minus alpha to the k, so k here is just 1, so one comparison. And you would get 0.05, which is what we've done all along. That makes sense to us. That's what we've been doing. We have our normal error rate. But now let's say we're doing two comparisons. Well, now we would have 1 minus 0.05 squared, and you actually get 0.0975, which is not 0.05. And we can actually see our type 1 error rate increased. And now if we had three groups, we would have 1 minus alpha, or 0.05, to the third, and we now get 0.143. So we can see that our error rate is increasing quite a bit. We're saying we want our type 1 error rate to only be 5%, but if we do three comparisons, which is what we would have if we had three groups, well, then we actually have a type 1 error rate of over 14%. Which is much greater than 5%. And this is a problem. This is like why we do ANOVA, why we're studying this chapter, is to try to get around this problem. So the ANOVA just tells us, okay, we have a difference, but now we're trying to figure out which difference. And we realize we can't just do a bunch of t-tests to see which groups are different from one another. So what we're seeing is that our probability of a type 1 error rate increases as we do more comparisons. So if we extended this out to say 1 like to 4, 5, we would just see this number go up and up. And so that leads us to the final topic of this chapter, which is to account for this multiple comparison problem. And what we're going to do is use something called the Tukey-Kramer procedure. So we're going to be doing this in Excel as well, but let's just take a look at it for a moment first, which is first we're just going to take the absolute difference in all the means. So we would take the average from Asia, subtract the average from North America, and we take the absolute value. So we always have a positive value when we do this. And we're going to do this for all j equal to j prime. All that means is two different means. So Asia, North America, Asia, South America, whatever. And then we're going to calculate our critical range. So CR is equal to Q alpha times the square root of MSW over 2 times 1 over NJ plus 1 over NJ prime. So Q alpha is the upper tail of another distribution. It's called the studentized range distribution with C numerator degrees of freedom and n minus c denominator degrees of freedom. So that might sound like a lot. Don't worry. We're just going to use software to calculate or to get that Q alpha. And we already have all of these numbers from earlier work. We already have the mean squared within, and we already have the sample sizes. So if two means are going to be considered significantly different, it's when the absolute difference exceeds the CR value. So if we're going to calculate the CR value, and we're going to see if our absolute difference is bigger than the CR value, then we're going to say that those two means are actually different from one another. So let's talk about the steps to the hypothesis testing. So let's talk about steps to performing hypothesis testing for the Tukey-Kramer procedure. So the null hypothesis is that mu j is equal to mu k and mu j not equal to mu k, and this is for all j not equal to k. So I'm just using notation here. So up above, this was using j and j prime. I'm just using two different letters now. So all it means is for any two. So that, again, this could be Asia, North America, Europe, and South America, whatever. We're just using j and k as placeholder notation. So step 2 is just to use the same alpha as we used in our ANOVA analysis. And then 3, we need to calculate this critical range value, which is calculated like this. Again, we're going to use Excel to calculate that. Step 4 would then be to use the critical value approach. So if our absolute difference exceeds this CR value, then we're going to reject H0 and accept the alternative. Otherwise, we just fail to reject H0. If this difference does not exceed the critical range, then we would fail to reject. Alternatively, we can use our p-value approach, which is going to be the same approach that we've used many times before. If p-value is less than alpha, we reject. If p-value is greater than alpha, we fail to reject. Okay, so I'll do this in a new video. We're going to do an example of how to do the Tukey-Kramer procedure.